All right, good morning. Today we're going to cover Zener diodes and a couple of analysis examples and a application example of Zener as a voltage regulator. So let's begin. There. Oh, this one is. All right, so we introduced Zener diodes last class. And okay, we spoke about how Zener diodes are used exclusively in the reverse bias, right? In the forward bias, they would work as a normal diode, but it would kind of defeat the purpose. The main point of using Zener diodes is that in the reverse bias, when it enters the reverse breakdown region right here, the voltage across the Zener diode is at a near constant level. So as you can see, the current can increase, but the voltage remains near constant. And that is because, of course, that it is operating in the reverse breakdown region. So few things to keep in mind. Zener diodes are used exclusively in reverse bias. So as you see here in the diagram, we have VD, diode voltage, and we have ID, the diode current. Now, VD and ID are always with the anode as a positive reference, right? But the Zener diode itself, we ignore the ID and VD. I will use it for this example, but then going forward, we'll exclusively use just Zener voltage, VZ, and Zener current, IZ. And Zener voltage and Zener current are both opposite of VD and ID. Okay, so VD has a positive reference here, the anode. However, VZ has a positive reference at the cathode. Okay, so we treat the Zener voltage and the Zener current as positive at the cathode, opposite of what the diode voltage and diode current would be. Okay, so that's the first thing to keep in mind. So I would say VZ would be minus VD and IZ would be minus ID, right? The second thing is, of course, that I pointed out last class is that in order for the Zener diode to turn on, the voltage must cross the breakdown voltage, which is, of course, the Zener voltage. So if Vin is less than the Zener voltage, the diode will not turn on. The only current that flows to the diode is the reverse saturation current. Okay, so we'd say the diode is off. When we use Zener diodes for applications, typically the output load is connected in parallel to the Zener diode. Okay, so first we will perform a Q point analysis using the load line method, then the piecewise linear model method, and then we'll apply it to the voltage regulator. All right.
Okay. Yeah. Copy here.
All right. Let's mute. If you see the characteristic that is provided here, in the forward bias, we are actually not concerned with the forward bias, of course. But the forward bias is shown as a straight line. Okay, and the reverse bias characteristic is actually shown with a slope. In real diodes, of course, that is the exact opposite. The forward bias actually has a slope, whereas the reverse bias is a near flat vertical line. Okay, this is just an exaggerated exaggerated slope for the purposes of this example. That is all. So let's take a look. VZ is given to us as 5 volts. RZ, the Zener resistance, is given as 100 ohms. And there is a series resistor connected between the source and the Zener diode, which is 5 kilo ohms, 5,000 ohms. Okay, so load line analysis, still the same. We apply KVL, write out a equation for the circuit loop. We have two unknowns in there, which would be the voltage and the current. And we choose value for one quantity to find the intersection point on the load line. Okay, so we plot the load line, which is of course right already done here. So let's see how we obtain those points. So we would apply KVL. And for this example, I will use VD and ID. And so if I apply KVL, I can write minus 20 would be equal to VD plus 5,000 ID. Okay. Essentially saying source voltage, of course, is divided across the diode and across the resistor. Now, if VD is equal to 0, meaning I want to find the point on the y-axis, VD is equal to 0, then ID is equal to minus 20 over 5,000, which gives me minus 4 milliamps, which is this point right here, minus 4 milliamps. Okay. So far, so good, right? And then we'd find the far point on the left, but we don't actually need to go too far to the left. What we want is to find a point that intersects our characteristic curve right here. So we simply choose the Zener voltage as the VD point. So for the next point, we choose VD as minus 5 volts. And with VD as minus 5 volts, I can write ID is minus 20 plus 5 divided by 5,000, and I'll obtain minus 3 milliamps. Minus 3 milliamps. Okay. So for minus 5 volts, I'll obtain minus 3 milliamps. Well, join the 2 points, draw the load line until it intersects the device characteristics, which is this point right here. From that point, we'd go to the graph and eyeball the values to determine the approximate values of that intersection point. So if we see here, the voltage, of course, is slightly larger than 5 right here. And so we can say it's about 5.1, 5.2, maybe 5.3. If we have a better graph, we'd be able to have a more accurate value. For now, either 5.2 or 5.3 would both be valid values. So the Q point is at 5.2 volts. And then the current is slightly less than 3. So you could say maybe 2.8, 2.9 perhaps. and 2.9 milliamps. Okay. Oh, and they are both, of course, negative. The minus 5.2 and minus 2.9. Thus, we find the operating point voltages and current for that Zener diode. All right, questions? Straightforward.
I have a question.
Yes, go ahead.
Um, I think I might have missed it, but where's the negative 2.9 milliamps from?
Oh, it's right here. The intersection point, the Q point. On the graph, we just draw the Q point and extend it to the y-axis.
So are we just kind of like
Right.
eyeballing those
Yeah,
numbers?
eyeballing the
Okay.
values.
Okay.
Exactly.
Thank you.
Yeah, eyeballing the values. And as I said, in this case, if I was to base my values solely on this graph, I would probably even say these could go to maybe 5.3 perhaps, and also minus 2.8. So if I presented something like this, I would consider both values to be correct because we are, again, as we said, eyeballing the values. Yes. How would we know where the values are without the graph? We can't because, I mean, the point of using the load line analysis is that we have a graph to begin with. So Q point is basically the operating point of the device, right? The device is VZ, Zener voltage is 5 volts, but the operation of the device is constrained by the external circuit, which is the supply voltage and the resistance. So if you think back to the beginning, not the beginning of this chapter, but the beginning of the diode analysis, load line analysis was the first one we did. And we said load line is basically describing the equation of the external circuit that is putting a constraint on the operation of the device. And so even though the Zener diode is 5-volt Zener diode, the slope shown here in the characteristic gives us a value of 5.2 volts or 5.3 volts. Okay, that is the constraint put on the Zener diode by the external circuit. And so that's the point of the analysis. We have a circuit or device characteristic presented to us, and then we have the circuit diagram presented to us, and then we want to find what are the Zener voltage values and what are the current values. So we're determining voltage and current using graphical analysis. Okay, any other questions? All right, let's look at the next technique, which is the piecewise linear model. In the piecewise linear model, we represent the Zener diode as a voltage source in series with a resistor that is known as the Zener resistance, RZ. So we have VZ and we have RZ, 100 ohms. Okay. And now we will simply work with VZ and IZ. Okay. We won't work with minus VD and minus ID. We'll simply work with Zener voltage and Zener current. Okay. So with a piecewise linear model, of course, we make assumptions, right? We make assumptions, and the assumption is that our Zener diode is going to be on. Now, if the input voltage is less than Zener voltage, then the diode will not turn on, as we stated earlier, right? So in this case, we see that the source voltage Vs is greater than Vz. Therefore, we can assume The diode is on. If the diode is on, then there is a current flowing through it, and therefore IZ must have a positive number, a positive value. So IZ must be greater than or equal to 0. So we analyze the circuit, and we analyze the circuit and we observe whether IZ is greater than or equal to 0. If that condition is satisfied, then our assumption is valid. Okay. All right. So let's write a KVL expression around the loop. And we obtain 20 volts should be equal to the voltage drop across that resistor, which would be 5,000 plus 100. So it's 5,100 ID, and then the Zener voltage, let's see, equal to 0. So ID, or IZ in this case, actually. So write down IZ is equal to 20 minus 5 divided by 5,100 gives me a value of 2.94 milliamps. Which of course is a positive number. Since IZ is greater than or equal to 0, our assumption is valid. Okay, assumption is valid. All right, let's take a pause. You write it down, think over it. Let me know if you have any questions. Any questions? Okay. Again, the techniques remain the same. Same thing that we did for the regular diodes. We apply the same techniques to the Zener diode, except that Zener is in reverse bias, and there are a couple of extra things to keep in mind. Okay. All right, then let's look at the main application for a Zener diode, which is used as a voltage regulator. So in a voltage regulator circuit, we have a load resistor RL that is always connected in parallel to a Zener diode. Okay, the output of the Zener diode is providing the output voltage VL. Positive reference is at the cathode of the Zener diode. Again, VZ is plus at the cathode, minus at the anode. And VL, of course, must equal VZ for the circuit to function. Okay. Now, Vin must be greater than VZ for the diode to turn on, and then that would give VL is equal to VZ. Okay. If Vin is less than VZ, then Vn is simply equal, VL is simply equal to Vn. Diode does not turn on, everything is supplied directly to the output load resistor. Okay, so let's label this as Vs, source voltage. Source voltage is supplying current Is, Iz, and IL are split off from Is. So to analyze this, let's apply KCL at the top. So you apply KCL at the top, we can obtain our equation. We will assume that the diode is going to be on because Vin is much larger than Vz. So since Vin or Vs is much larger than Vz, assume diode is on. And if diode is on, then VL is equal to Vz is equal to 5 volts. Make sense? Right? We apply KCL at the top and we obtain total source current is equal to Iz plus IL. Iz plus IL. Now we do nodal analysis, and so we express each current in terms of the node voltages. Is can be expressed as Vs minus Vz over R. Iz plus IL, which is VL over RL. Rearrange the terms and plug in the values to find Iz. Iz is equal to 20 minus 5 over 5,000 minus 5 over 5,000. Yes. Yes, absolutely. So let's talk about that just a little bit. Point being made in the class is that the Arduino, can we power the Arduino with a 12-volt source? Now, is the 12-volt source a battery or is it from a power outlet? 12-volt DC coming from a source. And can we connect a 5-volt Zener at its output and power the Arduino with that? It certainly is possible, yes. Now, the Arduino itself actually has voltage regulation built in. So it can take a 9-volt battery or a 9-volt source. And we connect it directly plug it into the Arduino. The Arduino itself has a voltage regulator. Wait, see. Let me take that back. It's not the Arduino. There is a voltage regulator board that comes with the Arduino as part of the kit. Okay, so we would plug our source, 9-volt source into that board, and the output of that board can go into the Arduino. It should just work. To plug in where though? No, in the USB port. Okay, so you're hypothetically speaking, if we just wanted to connect a Zener diode and power the Arduino that way. It should work. There are a few other considerations, meaning the load resistor, voltage coming into the Zener diode, the current coming in from the source, but theoretically it should just work. That's the answer. Yeah. Sorry for going on a tangent. But in general, as long as V in is greater than VC, it should just work. But let's discuss this in we'll talk a little bit about the point of connecting Zener in parallel with the resistor and what other factors can affect it. Okay. So let's finish this up first. IZ is 2 milliamps. And since IZ is greater than 2 or greater than 0, our assumption is valid. Okay. Assumption is valid, meaning the diode is indeed on and it works. And these are the values. Okay, yes. The diode is on, it's a short. Not quite. There is Zener resistance to take into account, which we haven't taken into account in this example. Zener resistance is 0. But what you are, I think I get your point. The answer would be yes. When it's on, it's acting like a voltage source. Okay. When it's on, it's acting like a voltage source, so you can consider it to be like a short if you wish. Yeah. But it's acting like a voltage source. But here's the point of how and why it works as a voltage regulator. Let's say VS is VS, the source voltage is 10 volts. Okay. If it's 10 volts, IS will have some value, right? IS will have some value which will be lower. That IS is being split between IZ and IL. Okay. Now, as VS increases, as VS increases above 10 volts, the total current being supplied from the source, IS, will also increase. Okay. What happens to the load current? Load current should also correspondingly increase, right? But that's where the Zener effect comes into the picture. If we connect a Zener diode between the source and the load resistor, the Zener will absorb the increase in current while keeping the voltage across its terminals constant. Okay. So for instance, if IL and IZ were both 1 milliamp at the beginning and source current was 2 milliamps, IZ is 1 milliamp, source and load current is also 1 milliamp. If IS, the source current, now increases to, let's say, 3, 4, 5 milliamps, the Zener diode will absorb or will permit a pathway for the extra current to flow through while still holding the voltage across its terminals constant, which is this portion of the characteristic. The current increases, the Zener will permit the extra current to pass through, but it will hold the voltage across its terminals at a constant value of Vz. And so IL does not get affected. IL remains constant, and thus VL also remains constant. Does that make sense? And there are a few equations that govern the working of this circuit. First one of those, and the most important one, is that the load resistor must have a minimum value. If the load resistor falls below that minimum value, then Zener voltage would not be able to regulate, or Zener diode would not be able to regulate that voltage. because if RL is lower, then IL increases. If IL increases, IZ decreases, and the Zener diode would not turn on. Okay. And so to find that value, we can simply take our equation from above. For regulation to occur, Zener diode must turn on. And for it to turn on, of course, Vs must be greater than Vz. And if it's on, then there is a current flowing through it, and Iz would have a positive number, a positive value. And so we'd simply take the equation from above and plug it in here. So Vs minus Vz or R minus Vz or RL must be greater than or equal to 0. We rearrange the terms, and we obtain Vs minus Vz over R should be greater than or equal to Vz or RL. And we can take RL to the other side and find that RL must be greater than or equal to Vz or Vs minus Vz times the series resistor R. So in order for the Zener diode to turn on, load resistor must have a minimum value as given by this equation. This would be known as the RL minimum. Okay, RL minimum. All right, questions? Any questions? Okay. So in this example, RZ, Zener resistance is given as 0. Let's take a look at an example where RZ is not equal to 0. So here, oh, hold on. One of my pages went missing. Okay. So this next example has RZ value of 100 ohms. So we are given a VZ of 5 volts and RZ value of 100 ohms. Let's see how this affects the output voltage. The question being asked is then find VL and find the Zener current IC. Everything else is the same. Source voltage Vs is 20 volts. Current Is is flowing through, is coming from the source, split between Is and IL, right? So we follow the same approach. We'll assume that diode is on because Vin is greater than Vz. Apply KCL. Source current is split between Zener and load resistor IL. And we'll plug in all values in terms of VL. So Is is Vs minus VL or R. Iz can be written as VL minus Vz over RZ, and IL is, of course, VL over RL. In this instance, VL is not equal to VZ. Okay, VL is not equal to VZ. So plug in the values. Vs is 20 minus VL divided by R. Plug in the values and solve for VL. So multiply everything by 5,000. You get 20 minus VL, 50 VL minus 250 plus VL. That gives me 270 is equal to 52 VL. And therefore VL is equal to 5.1923 volts. Okay, 5.1923 volts. So the Zener let's take a pause and you have questions, and then we'll talk more about the circuit. Okay. All right. So the Zener resistance, of course, is part of the diode. It's the diode resistance. Okay. It is physically, we cannot physically separate out the Zener resistance. We cannot separate out the diode resistance from the diode voltage. Okay? It's physically the same component. But schematically speaking, we draw it as a resistor in series with that Zener diode. So when we connect any load in parallel with a Zener diode, we have to take into account the Zener resistance. Okay, the voltage, the diodes are fabricated to take those resistances into account. So even though the Zener resistance is rated as 5 volts, the output voltage is 5.19, 5.2 volts. Okay, and this is something we'll simulate in the, we'll simulate and perform in the lab next week. All right, so our job is not yet done. We still need to find IZ. So IZ would be equal to point 1923 over 100. So it's 1.923 milliamps. And since IZ has a positive value, our assumption is valid. Assumption is valid. Okay, questions? Any questions? Okay. All right, so we're talking about regulation. want to just bring in two parameters to describe regulation. Regulation can be of two kinds, load and line. Load regulation basically means how well is the Zener diode able to hold the output voltage constant if the load resistor changes. And line regulation is how effectively can the Zener diode regulate the output voltage as a function of the input line voltage. Okay, so we have load regulation and we have line regulation. Load regulation, of course, is change in output voltage as a function of the change in load resistor. So in this case, the load current. And then line regulation is change in output voltage as a function of change in source voltage. Okay. In terms of the components, there is an equation that can be given by minus RZ for R. And then here it's RZ over R plus RZ. Okay. At its most basic, we can put it all together to create a decent power supply. Okay. There are, of course, depending on your application, there are a whole lot more factors that we can, that we can look at. But starting from our bridge rectifier circuit all the way to the end of the Zener, we can create a very basic power supply by connecting it all together. Okay. And so let's see, 54. Let me draw that right here. Suppose we want a DC output anywhere from 2 to 10 volts. Okay, 2 to 10 volts. Then we would take a transformer which of course is connected to the power outlet, 120 volts. And we step it down to perhaps, let's say 15 volts. Okay, 15 volts. We would connect that to a bridge rectifier circuit. And the output of that bridge rectifier can be given to a capacitor. Let me put a series current limiting resistor. Okay. Give it to a capacitor that is perhaps 10,000 microfarads, very large. The output of the bridge rectifier would be approximately 13.7 or 13.8 volts. Goes into the capacitor, which reduces the AC ripple. Let's say ripple was about 100 millivolts. And then we connect our Zener diode. And our Zener diode could range anywhere from 2 to 10 volts, RL. And VZ would go anywhere between 2 to 10 volts. 10 volts might be a stretch depending on the values of RL and the value of the series resistor, but it definitely would work for anywhere between 2 to 7, 2 to 8 volts, because our input voltage coming from the bridge rectifier is sufficiently large enough. Okay, so you have the rectifier circuits, you have the filter capacitor, and then we connect the Zener. The output of each stage leads us to having a near constant flat line at the output. And this is basically how most power supplies are constructed. Going on a bit of a tangent, in real life, there are actual voltage regulators that we can buy, 7800 series, 7900 series, and they come in all voltage ranges. Okay, so each voltage regulator or each Zener diode that we buy will have a input range that will be on the manufacturer's spec sheet that describes, that describes the range that we can actually use the Zener diodes. Okay, and so this is the experiment for lab next week, and that's where you'll actually look at the spec sheet and become familiar with many of the terms. Okay. All right. Announcements. Quiz as usual on Monday based on the material we have done this week. There will be a homework based on the Zener diode, and I will post it shortly after I come back from my appointment. And there'll also be like a short reading assignment. Other than that, not too much work burden over the weekend. It'll be like one problem, maybe some short answer questions perhaps, but students should be able to knock it out in half an hour or less. Again, as I posted the announcement, I stated earlier in class, I have an off-campus appointment and then I have a seminar, and so there's no office hours today, but I will be available again later this afternoon from 4 to 5. Okay, I have a seminar workshop from 12 to 4, but again, I'll be available from 4 to 5 if students need to see me. And of course, I'm always available via email. Okay. All right, so we'll end class here today, and I will see you all on Monday.